Hello, grade 12s. In the next lesson, going to go over bond energies, another method of calculating the enthalpy of a reaction, right? So let's start. Okay, so the idea behind bond energies and using that to calculate the enthalpy or the molar enthalpy, which is probably best to say in this case, um, stems from just the idea that a reaction, the energy difference of a reaction is proportional, directly proportional to the bond energies of the reactants and the products. And I'll define bond energies in the next slide, but a reaction essentially involves the breaking apart of your reactants, right, to form new bonds in your products. So if you add up all of the bond energies, all of that is going to give you the energy difference, enthalpy, right? In this example, see that, well, in this diagram here, see that a hydrogen atom and an oxygen atom are coming close together, have a certain amount of energy, right? Certain amount of both of them of potential energy. When they come together, they want to come together, they want to react. So when they do create an OH bond, right? And there is still some distance, of course, between them, right? 96 picometers here. Um, they react because they want to, as we looked at in our last unit, they want to achieve a lower energy, lower potential energy. And when they do achieve that, all that difference and in energy is released, right? And we'll look at this bond energy then. A similar amount of energy perhaps might have to be put in to break that if that were then involved in another reaction. So uh, that is what bond energy is. So it's the amount of energy required to break 1 mole. So it's measured per mole of a certain type of bond between two particular atoms. And I'll show you a diagram, a graph, rather a table that goes over those different types of bonds. And this has been measured experimentally and tabulated for research. You don't have to memorize any of these values. I'll give them to you on a quiz test exam or wherever you need that. Okay, so an example of how you might read a bond energy value is here. So to break a hydrogen-hydrogen bond, you need 436 kilojoules per mole, right? And that table is here. So it's an extensive table straight from your textbook. You can see that it takes two things into consideration. It is between unique or between different types of atoms, so hydrogen, 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 fluorine, carbon, 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 hydrogen. Also, then the type of bonds. Right, so here are all to the left, all your single bonds, and all to the right over here are your multiple bonds. So between carbon and carbon single bond, it's 347 kilojoules per mole. But between a carbon-carbon double bond, we have 614 kilojoules per mole is required to break that bond. Okay, but there is a little bit of background here that we need to look at. So it's to calculate those bond energies. It's actually an additivity of bond energies that is considered. So, for example, methane from our first unit, some of your favorites, must have been your favorite unit. Okay, it is mine actually. Well, it's time for the next one. Um, so the first hydrogen breakage requires 435 kilojoules per mole. And once that's broken, the next hydrogen requires a different amount, 453 kilojoules per mole, and so on. The next one requires 425. The next carbon hydrogen bond requires 339. So when we are looking at compounds with multiple bonds like this, so carbon, hydrogen, there's four of them, we add up all of the energies required to break all of these same bonds but different bonds, right? Four of them, they are all the same, but there are four of them. We add them all up and divide by the number, and that gives us our average. So therefore, it requires 413 kilojoules per mole to is needed to break a carbon-hydrogen bond. Okay, so that's how these values are tabulated using the additivity of bond energies. Okay, so the idea is this. We're going to have the sum of all the energies required to break the old bonds. So that would be referring to your reactants, right? So this refers to all of your reactants. We're going to add that then to the sum of the energies released in forming the new bonds of your products. So add them all together. Now the thing here is, because energy is released in the creation of these bonds, it's going to actually be a negative value. that means your real formula is going to look more like this. So enthalpy, right? Enthalpy of your reaction is then the sum of bonds broken minus, so this is the difference here, minus the sum of the energy required when you're forming those bonds. Energy required, released, I should say, released when forming those bonds. Okay, so of course, taking your mole values into consideration here, sum of the reactant bonds broken, right? Reactants minus products, different from other formulas we've seen, minus, right? The sum of all of the energy required to form the bonds that exist in your products, right? So this really is the formula that we will use, right? And we talked about then the idea behind that and the theory behind that, which hopefully you're comfortable with or will become comfortable with, right? So an example, determine the enthalpy change for the formation of hydrobromic acid from its elements. So hydrogen gas, bromine gas, 1 mole of each produces 2 moles of hydrogen bromide. There should be an AQ here for it to be hydrobromic acid. Okay, so this is what we're looking at. We're looking at adding, so all of your reactants, the sum of all of the bonds that are in your reactant. So hydrogen, bromine, the number of moles have to be considered minus the number of moles of hydrobromic acid, right? This is the type of bond. It's a hydrogen-bromine bond. This is a bromine-bromine bond. This is a hydrogen-hydrogen bond. Then plug numbers in, plug your values in. So I had to put it to 2 lines here. I'll reveal your products in just a bit, but these are your reactants to begin with. We have 1 mole of hydrogen-hydrogen bonds. And going back to your table, 432 kilojoules per mole. Let's go back to our table. 432 kilojoules per mole of hydrogen-hydrogen. Okay, so that's where those values come from. Again, you don't have to memorize that. I will give you that. I will embed it into a question so that you can refer to easily. Okay, we're going to add then this value here. That's a bromine-bromine. There's just one, there's a coefficient here of 1, so there's 1 mole of bromine. And that's 1 mole times, this came from the table again, it's 193 kilojoules per mole. And we're done there. This is then the sum of all of your reactant bonds minus the sum of your product bonds. So in this case, it's not, we don't have a coefficient here of 1, we have a coefficient of 2. So that 2 has to be taken into consideration here. 2 moles times, this comes from your table. And a little bit of calculator fun there, and we get 101 kilojoules. Notice that mole cancels out. That's a negative also, I should say. Of course, you can see that. So mole cancels out mole. Add all of this, subtract, and you get negative 101 kilojoules. Right? And that's how you figure out the enthalpy using bond energies. Right? I believe question 2A from page 313 in your textbook actually gives you an answer of negative 158 kilojoules. I believe there was, you're looking for an answer to this question. It's a good question to do. Give this a try. Ask any questions. I will post videos going over your questions from your textbook or from worksheets. Right. Page 313 is your home fun. Questions 1 to 5. This is, I usually end videos right here, but this is a great little comic strip. If you recall the story of the 3 bears, Goldilocks and the 3 bears, that's it. Okay, so Goldilocks walks in, she trespasses into the house and starts stealing their things, stealing their food, using their stuff. Strange story, but essentially one of the most memorable parts, besides her doing all that theft and trespassing, is that she encounters some bowls and she says that the big bowl is too hot. Then also says the medium bowl is too cold. But then I guess the story was trying to be cute and saying that the small bowl was just right. Now, that can't be. That can't be. Why? Consider that. Question in class. We could talk about that online. Hope this video helps.